All right, back to 100 Days of ML. It's day 88. And today I'm going to be continuing with the Machine Learning Berkeley reading list, the beginning guide. They have a list of papers here. I'm going to finished up EfficientNet yesterday. And today I'm going to continue with YOLO, very important, one of the most important detecting models in computer vision. So I don't think I've read this model, but I've heard of YOLO before, and I've used um, a section of it before in one of my research papers. So we'll see how this goes. So same thing, we're gonna use the strategy defined in the MIT AI lab, how to do research. First, gonna read the abstract, gonna figure out what the paper is basically about, and then figure out where the important sections are, read that first, and then decide if you want to go back and then read the entire paper. That way it makes the whole process of reading the papers efficient and fast. Okay. I think I have to upload this into my iPad, so I'm going to go ahead and do that right now. What's going on here? For some reason, I'm not able to send this to myself. Yeah, I'll just email it to myself. Okay. Let me rename the file, call it YOLO. You only look once. Real-time object detection. All right, go ahead and read the abstract. Okay, so I guess the main research done here is the fact that they framed the object detection as a regression problem to spatially separate bounding boxes and associate class probabilities. And this process has led to a whole detection pipeline into a single network, which can be optimized end to end. So we'll see what that actually means in the later on sections. And YOLO makes localization errors, but is less likely to predict false backgrounds, false positives on backgrounds. So it's extremely fast, and I think what they're trying to go for is the fact that it operates in real time and has a incredibly fast inference time. So let's see, where do they start? Inference imitation training. I think it's right here. I think 2 and 2.1 is where most of the work starts. Okay, I'll start with section 2, which is about unified detection. Wow. Okay, let's talk about the unified detection. So what they're saying is that they unify separate components of the object detection into one single neural network. And I think the process of doing this is by taking an image, cutting it into an S by S grid. So we have an input image here with a dog and a bicycle, and it cuts it up into S by S. And S could be arbitrary numbers. So each cell predicts B bounding boxes. And we can see that here. So bounding boxes plus confidence. So there's a B amount of bounding boxes produced in these grids, S by S grids. And along with their XY coordinate and width and height, XY width and height, they contain a score called the confidence on which basically indicates like what's the confidence that a certain object exists in that bounding box. So we have 5 predictions in each bounding box. In addition, each grid cell also predicts C conditional class probabilities. So we can see that in this image here, the model. S by S, we have the bounding boxes, confidence, we just talked about that. And we also have class probability maps. And it's the probability that the grid cell contains an object. And we can see blue here for like the dog, red here maybe to indicate that there's nothing here, or green, nothing here. And then the yellow here is trying to indicate the fact that, there's a bicycle moving around here. And using the bounding boxes confidence and the class probability map, it combines the two scores through this prediction metric right here, and finally produces final detection. So what they say is they multiply the class probability and the individual box confidence predictions. Right here. So right here, this probability is the class probability map. It's being multiplied with the object, and this IOU is the confidence. So I think this is probability of the object and probability of the class conditional of the object multiplied by IOU, truth over prediction, and you get this equation here. I'm a little confused. Class conditional object? Okay, anyways. Then moving on, the final prediction is a 7x7 tensor. Talk about the network design, how they set it up. So it was inspired by the Google LeNet model. And what they did was take 24 convolutional layers followed by 2 fully connected layers. And instead of the inception modules, they used a 1x1 reduction followed by a 3x3 convolutional layer. So, and the fast YOLO just uses a smaller architecture. The final output is a 7x7 by 30. And you can see a nice description of the architecture in this diagram right here. Yeah, I kind of want to practice by like coding this using TensorFlow from scratch instead of kind of importing the. I'm pretty sure TensorFlow has some sort of YOLO, or Keras has some sort of YOLO architecture already inbuilt. But what I could do is try to practice on building these networks just using the fundamental Keras libraries, like just using sequential layers, and build the whole architecture by using these layers. That would be a fun project to do. Maybe I'll take it up. Okay, let's go to training and see what they have done. Okay, let's see. So they started off by pre-training the convolutional layers on ImageNet, and they used the darknet framework for all of the training and inference. And moving on, they use a linear activation function followed by for the final layer, and for the other layers they use a leaky linear activation. So you can see that here. And for the optimization, they sum up the square error and maximize average precision. So they list a bunch of different parameters that they used for training. And what it does is basically predicts multiple bounding boxes per grid. And in order to do that, they basically take the highest value for each section, combining the bounding box confidence and the class probability map. So they decide which one to choose for that section. And that's given by this complicated equation right here. It basically just takes a summation, and whatever is the highest, it just takes that. It's also denoted as a loss function. So what they're trying to optimize. They ran it for 135 epochs and added in dropout layers and data augmentation for overfitting at the rate of 0.5. So that's the training. Kind of want to read more. So I think what I'll read is limitations and comparisons to other detection systems. Okay, I mean, the model struggles with groups of objects, groups of small objects, and a little more other things that come into play. The main source of error is basically the incorrect localizations. It's pretty cool. So what I'm going to do is try actually to implement this in using TensorFlow. So I'll start with EfficientNet, try to implement it, and then go down this list. Let me update. So it's kind of funny. I mean, I started this series by trying to focus mostly on ML ops, but then I finished like 3 textbooks and then had nowhere else to go. So going back to research. But I think essentially like doing research is pretty important because it introduces the fundamental ideas of like the probability statistics that are really crucial in ML ops. Especially because the models that like people are implementing in their companies aren't state of the art deep learning models. They're just basic statistic models like linear regression and whatnot. So having a strong basis in data science is very helpful if you're going to go into like an engineering route. But at the same time, who knows what will happen in the next 5 to 10 years in the industry because of the fact that, things are growing exponentially, and these models could be ready to run on everyone's devices in maybe next few years or so. So we got to keep our eyes open for this. And with that, I'm going to conclude for today. We'll be back tomorrow to try to figure out how to implement EfficientNet if it's possible. Otherwise, I'll try to implement YOLO, and I'm pretty sure YOLO is definitely more possible to implement. Okay. All right.